physics. This is the biology. They put us in this room.
Small rat snake.
It's a snake?
A little one. No. The big one is right behind you.
I hate snakes. I'm just not even going to turn around.
Don't turn around. And see, don't, and we're talking chemistry today, not biology, so you guys we got to look up here. Because we will have it on video. We'll know exactly who's not paying attention.
All right, ready? We are ready.
We're ready. Yes. What's the question?
Can we touch the snake?
No. We're doing chemistry and physics in here. We'll see. Good morning, everyone. I guess it's still morning for a few more minutes. I'm Bill Waberson. I'm a nuclear engineer. I work at Savannah River Site. And today we're going to take a journey to the center of the atom. What's in the center of the atom? Do you guys know? Nucleus. I'm going to try to get you guys to talk, so you guys are going to have to help me here, okay? Nucleus, I heard that. So we have a symbol for the atom. If we get rid of electrons, did you have electrons earlier? I guess you learned about electrons, periodic table and things. Electrons for nuclear people aren't important. We are nucleus is what we care about. So we're going to learn about nucleus. What's in the nucleus? Protons and neutrons. Very good. We're going to get to that. This is sponsored by Citizens for Nuclear Technology Awareness and the American Nuclear Society. And I built this kit that you see here, so my name's up here as a sponsor as well with the American Nuclear Society. So first we're going to do a review of the atom. Now you learned this in elementary school, I'm certain of that, and hopefully in chemistry you had it as well. So let's go over this together. There are two parts to the atom. There's a nucleus and an electron cloud. What are in the nucleus? We already said. Anybody else? What are parts of the nucleus? You guys, tell me. You don't know? You can read it. Come on, help me. This is being videotaped. They all know you're being quiet. Come on. It's a proton and a neutron, right? Protons and neutrons. What's in the electron cloud? Electrons, thank you. The protons and neutrons, they have about the same size. They're one atomic mass unit in size. Protons have a charge of +1. Neutrons have no charge. They're neutral. That's where they got the name neutron. Electrons have a charge of -1. They balance with the protons, but their mass, they're very tiny. 1/1800th the size of a proton or neutron. In reality, if they were, this was a model of the atom, these would be so tiny you wouldn't see them, the electrons flying around the outside. So the mass of an atom is really made up of the protons and the neutrons. Now, let's say the protons are red and the neutrons are blue, these ping pong balls. If I took two protons and tried to push them together, would they go together? Why? Because they're the same. That's exactly right. Like things repel and opposites attract, right? What if I took a neutron and a proton? Could I put them together? Yes. They're not opposite, but this has no charge, so it can go right in. And they get very close. The strong nuclear force takes over, and boom, they smash together and they stick together. Now, can I stick a proton to this neutron? I can. And this neutron acts like the glue that holds an atom together. Does that make sense? And so when you have too much glue or too little glue, what happens? Say you had 2 blocks of wood about this big, and you didn't put enough glue and tried to glue them together. What would happen? It would fall apart. What if you put 6 inches of glue between them? I know the balls are moving. You guys, I see you're focused on that. What if you put 6 inches of glue between them? What would happen? Would they stick together? The glue would come apart, actually. The glue itself breaks apart. So they don't, and atoms do the same thing. When they have too much glue or too little glue, they break apart, and that's called radioactivity. That's when things become radioactive. Does it make sense? And so we're going to talk about radioactivity here in a second. What is this? It's the periodic table. That is correct. Now you can, if you look, it has an unusual shape. It's shaped kind of like a U, and the lanthanides and actinides, they normally belong in the middle of the chart, but they have broken them apart and set them down the side. Mainly that's so it fits on a page of a book. That's why it's written that way. But why is this shaped in the shape of a U? Why is it in that shape? Do you know why it has this unusual shape? Because it's arranged by the number of electrons. These are called families, and they come down in the number of electrons. That's how they're ordered. And so as nuclear people, we really don't care about electrons. Electrons actually just follow the protons, but we care about what are called isotopes. Now, hydrogen is right up here in the corner, hydrogen 1. And if you think of this as a Scrabble tile, it kind of looks like a Scrabble tile H. There are actually a whole bunch of those tiles stacked on top of each other. They're called isotopes. There are multiple kinds of hydrogen, and we're going to demonstrate that here shortly. We mentioned the term isotope. What is an isotope? Does anybody know the definition of an isotope? What an isotope is it has the same number of protons but a different number of neutrons, a different mass. So if you look at, these are 3 types of hydrogen. If you see this first one, it's hydrogen 1. It has 1 proton and 1 electron. How many protons does this one have? 1 and 1 electron. How many protons does this one have? 1 and 1 electron. So they're all identical electronically, chemically, they're all hydrogen. But we put a little bit of glue on this one, 1 neutron, it becomes hydrogen 2, because it has a mass of 2 now. This has a mass of 1. This is hydrogen 3. It has 2 parts glue on it, the neutron, and it becomes radioactive at that point. Tritium is radioactive. We make that at Savannah River Site, and that's where I work, the facility that makes and recycles tritium. And so we have those different isotopes of hydrogen. This periodic table shows, whoops, I went back, excuse me a second. That periodic table shows the number of isotopes in the shape. You can see up here in hydrogen, most hydrogen is hydrogen 1 with a little bit of hydrogen 2. Most helium is helium 4 with a little bit of helium 3. Down here, mercury has, see all the different colors, it has lots of isotopes in it. So this is a different way the periodic table is shown. Now, you're going to have to pay attention to this next couple slides, because the hands-on activities we're getting ready to do use these slides. You're going to have to be able to do some math. This is the standard nuclear notation. It has a X, A, and a Z. The X is the chemical symbol. Down here you can see that carbon. Down at the bottom there's carbon C. That's the symbol. The bottom number Z here is the number of protons. So carbon has 6 protons. This number A, this letter A, is the number of, it's the mass, the number of protons and neutrons. So they're added together. It's the number of protons plus the number of neutrons. So how many, on this carbon, 6 carbon 12 is how we say it, how many protons are in 6 carbon 12? 6. How many neutrons are in 6 carbon 12? You have to do the math. You have to subtract one number from the other. So it's 6. On this one, it's 7, because it's 13 minus 6. The 6 always matches the carbon, so sometimes we drop it, just so you know. Okay, we're going to practice as a team. You ready? How many protons are in 1 hydrogen 1? 1. I heard 1 from a couple places. Very good. Very good. There's 1. How many neutrons are in 3 lithium 7? I heard 4. Anybody else? 4 is the correct answer. You do the subtraction. How many protons are in 8 oxygen 17? How many protons are in 8 oxygen 17? Is it 8 or 9? I hear both. Which number is protons? It's the bottom number is the number of protons. So it's 8. Very good. How many neutrons are in 1 hydrogen 1? Anybody over here? I hear 0, and I see 0. 0 is the correct answer. Got to do the math. All right. Now, what we're going to do is I want everyone to come up, and let's stand over here at this table. Come on over here. Stand around on this side of the table. On that side as much as you can. Of that one under. Now this is a view of the periodic table. And we put the lanthanides and the actinides in their proper space. Get up closer to where you can see. And let's let the camera have a view of it too. So that's good. So this is the lanthanides and actinides are in their proper place here on the table. Now this is a little bit different periodic table because there's a number below it, and that's the number of isotopes. And so we're going to show you that in a minute. We left some blank spots on here, so I want you guys grab a tile, and I want you to pass them around. And there's some of you are going to get more than one. Here, pass them in the opposite direction. Grab one tile, and grab a second one if a stack comes back your way. Grab a second one. A couple of you get two. And then put them on the periodic table. Now, if you have uranium or mercury or copernicium, they're down here. The rest of them are on the blank spots. There you got hydrogen in the right spot. Very good.
Does that say 12?
The sodium goes there. Magnesium goes right there. There you got it. It goes right. That perfect. Neon is good. Yep, there you go. Very good. Very good. Who has uranium or copernicium? The uranium is here. It goes over here. The uranium one goes over here. I see it right there. Put the uranium here. And mercury's right in front of you. See the HG? And then that copernicium is down here, right here. The rest of them should fill in. You have 2 spots left. That's right. That's right. Very good. Very good. So you filled in the periodic table. Now I'm going to show you something. This is the number of isotopes for mercury. And this is the number of isotopes. Remember I said there's stacked up tiles? This is copernicium. That's uranium, mercury, and copernicium. Now what happens is they're colored. The green ones are stable. They're not radioactive. The blue ones and the red ones are radioactive. The blue ones are long-term radioactive, so they're relatively stable and we can use them. The red ones don't even last a second. They disappear really fast. They're unstable and we can't use them. And so this is how many there are of these isotopes. What we're going to do is if you look over that table over there, those are the isotopes for all of the other tiles. And so remember the one that you put down, and we're going to go over here and sort these out and put them on this tile as well. So come on back over here. So what I want you to do, come over here, come in here, everybody, in here. We're going to take these stacks and we're going to sort them. Now if you look at this, the fluorine, 9 fluorine 21, see the 9 is the atomic number. We're going to put that where the 9 is, just like that. So we want to take all of these and let's just sort them. You can just pick them up and we're going to put them on these spots of the table over here until they're all sorted. And when you're done, we'll start stacking them, but after we sort them. Go ahead and sort them. When all of them are cleared from the center table, we're going to start sorting those stacks numerically. So I'll describe that as we get closer to the end. Okay, when you're done with your sorting, go stand next to the number of one of the elements that you placed on the table. Go stand next to one of the elements that you placed on the table. And then stack them numerically with the lowest mass on top, the highest mass on the bottom. Stack them in order numerically with the lowest mass on the top and the highest mass on the bottom. And when your stack is done, you can come over and place it on the periodic table.
Place on that one?
Yep. Just like we did with the other ones that are stacked. What do you have?
Beryllium.
Beryllium. So you'll come over here and place it under that and put the white towel on top. And try to get them nice and easy because other people are nice and straight because others are going to come stack next to it. And then if you want, go grab another one that someone else is not on and stack that as well. Okay? So you'll come over here and stack it under the nitrogen and try to get nice and straight because others are going to stack around it. There you go. Once you've got your stack done, go ahead and let's put it over the table. And you can take these and set them over here. Try to stack them nice and straight so others can get theirs around. What do you have? Oxygen, so it'll go right there next to the nitrogen. Fluorine will be next to his oxygen when he's done. What do you have?
Carbon.
Carbon will be next to the nitrogen over here. He's bringing them all over, huh? What do you have? Put the white one on top. Let's go ahead and put this one on top real quick. There you go. What do you have? Hydrogen? So send them there. It's okay. If they're out of, it's all right. If just have them in order. Set that on top. What else do you have? Helium's over there. So once you get your stack done, let's go ahead and put it on the table. Lowest number's on top. And put the white one on top.
Some of the hydrogens with boron.
All right, we'll move it and we'll put it in the hydrogen. Those aren't in order, are they? Yeah, there should be a green one on top. Reorder those. We're getting close, and then when you're done, come back over. We got more to do over here. Aluminum right there.
Where's phosphorus?
It's over there.
Over here?
Let's get that white one on top.
Oh my gosh. Do you have any idea how hard it's going to be to
There's a phosphorus. You can break it in 2 stacks. It's a little easier if the stacks are too tall. Are we close? We got one more to get in there, phosphorus, and then we got another activity to do. Okay, you can put one stack in and then put that on top. Help her slide those in. All right, so let's all gather on this side of the table and spread around, right? Just spread around. There you go. Now what happens is if you look, I mean, if we stacked all of these up, they get more and more until they get to mercury, and then they get less and less all the way down to copernicium. And so there'd be a lot if we did the whole periodic table. So we only did it up to potassium. Now what you'll see is there's a symmetry to that. You can see there's green and blue on either side and red on either side. But if I wanted to learn about this magnesium right here on this chart, it's not very helpful because it's underneath the stack. You'll also see that this number up here on the top is like 24.3 for magnesium. It is the average of the naturally occurring isotopes. It's not the real, the rest of them are all whole numbers. That's an average. That's why it's got a decimal. But, so a nuclear person doesn't use this chart. We use this chart over here. So I'm going to show you how this works. Then it's our next activity. So we'll just grab, let's all come over here and stand around this table, just around it, and leave this side open. So let me describe this chart. This is called the chart of the nuclides. This is what nuclear engineers use. And so the y-axis is the number of protons, which also match the element name. Can you see that? The bottom is the number of neutrons. So I have here 1 hydrogen 1. Remember we did this math before. How many protons is it? How many neutrons is it? I heard 1 was the answer. That's correct. How many neutrons is it? 0. So let's put it on the table. Where does that go? It goes where 1 proton is and 0 neutrons. So put it on the right spot of the table. 1 proton, right there, and 0 neutrons. This is a neutron. 0, neutron, 1. So how many protons does it have? 0. How many neutrons does it have? 1. So put it in that spot of the table. Now I have 14 silicon 43. How many protons does it have? How many neutrons does it have? We got to do the math. 43 minus 14, right? Anybody have it yet? 31. Is it 31? No. 29. 29. So we'll do it. We come over to 14, and we slide down here until we get to 29. So I come, am I on 14? And 29. And so we place it there. So the stacks that you did, I want you to take those stacks and put all of the colored tiles on here. Leave the white ones over there, but put them all on this chart. So go ahead and do that. You can leave the white one behind. Just grab, don't leave those ones alone because those are glued together. So grab a stack and grab any stack. You can grab these magnesium ones, leave the white one behind, and just set them in the right place over there. Very good. So go ahead and place them. So you put them on the line.
So this is 11.
So
It's
it's
15 and 11.
So you go 15 and 11.
So it would just 31, 13.
No, you have to do the math. What's the difference between them?
Oh, you have to subtract.
Right, and so that's the other line. And then you just, once you get one down, they'll all be in order after that, typically. So like this one, 30 minus 13 is what?
I gotta do that on my own. I can't right now.
You got it. Find one that,
Oh, 20.
no,
What?
do that one. That one you can do the math easy.
No, I suck at math. I'm just gonna.
No, that one is easy there. 33 minus 13. It's the 0. But then once you place them, you can set them down. There you go. That's exactly right. But you'll see they should go in order, right? They should go in order once they start going. There you
So
go.
this is 16 and 11.
16 and 11. There you go. Okay, if you're not doing one, grab some more. Grab some more if you're not doing some. There you go. You'll start to see as you place them, there's an order, and it's relatively easy once you get the order. There you go.
I don't get.
There's a couple more argon and neon left over there, so go ahead and get those. There you go. That's it. Perfect spot. Exactly right. You'll start to see there are patterns, right, on how it goes together. You'll start to see those patterns. Yeah, you can start. Oh, you got the potassium, chlorine. So they'll all be going in here.
40 now. Is it 20? Yeah. I'm just putting them in order. Number up top.
Okay, thank you.
order, Haley. I know, but not in order. Oh.
I'm just putting them in order.
Put them in order
Yeah.
really fast.
Look, this one, the 30, the 40 will go there because they'll go in order this way as well. See that? There you go. Okay, we're close. We just got the chlorines left to go and some argon.
Good work, Haley. Yeah.
Now this one doesn't look, they got to come down one like that. There we go. All right, let's start to look at the patterns. I want you to describe the patterns you see. Go ahead and finish. See, I tried, by putting them in order before, it should have made it a little easier. Go ahead and keep going. You're almost done.
I think I'm missing one.
Now, what patterns do you see? Explain the patterns that you see. What patterns do you guys see?
They increase the number
From which way?
left to right.
They increase the number from left to right, which makes sense, right? Because they have a constant number of protons and the neutrons increase by 1 each time. Do they increase the number in another direction? They increase the number going up as well. Look, 31, 32, 33, 34. You see that? Can you see they're a constant number at a diagonal? So you can see that. How about color-wise? Do you see a pattern color-wise?
It's like a periodic table with a step.
Yeah, it's, what colors do you see? Is there a pattern?
Red and blue is less green.
Yeah.
Green is like,
Green light.
it separates the blue.
The green is like a line down the middle that separates blue on either side, and then there's red outside of that. That green line is called the line of stability. That's what nuclear engineers actually focus on. That's a natural phenomena. There's a balance. Remember I talked about the glue on the balance of glue? That's the right amount of glue that are stable. If you get out of balance, they become radioactive. That's the blue ones on either side, and then very unstable are the red on either side of that. What nuclear engineers do is we try to take advantage of that. Look, point at carbon-14, somebody. Carbon-14, have you ever heard of carbon-14? Carbon-14 is used for archaeological research. It's used to determine the age of fossils. They know that because how much carbon-14 is in them when they died and how long ago it was. They can go back to 60,000 years based on carbon-14. That naturally occurs in nature, and so we look for things that are off the line of stability naturally and watch how they go back to the line of stability. Or we can take something like fluorine-18, which we make, has a very short half-life, but it's used in medicine for positron emission tomography, that we push it off the line of stability, and when it comes back onto the line of stability, we take advantage of the energy it gives off. So that's what we do as nuclear engineers. So now as a team, we're going to need to break up into 4 teams. So there'll be teams of 3 or 4. So break up into teams of 3 or 4 and into 4 separate teams.
Why does beryllium not have blue beside the green?
So
It doesn't like to be stable. You can get a whole degree just understanding beryllium. It's really interesting.
4 and 3. Okay, got your groups?
Okay, group number 1. You guys get hydrogen. You guys get boron. You guys get carbon. And you get neon. And so we're all going to go out to the lobby. Let's everyone follow me, and we're going to do the next exercise. So team number 1, come stand over here. Just stand there for a moment. You're in team number 1?
No.
Team number 2, stand over here. What team? Who's in your group? Your group stand over here. The next group stand over here. And then one group will stand over here. Okay. Now what we're going to do is we're going to do an exercise. Now this is called the interactive nucleus, and you can come here it's open all the time, and you can come here on your days off and do this. So what we're going to do is, we want the TV camera to kind of see this as well, so if you can kind of spread out and stand like by the proton or by the neutron so they can see the middle. The blue are neutrons, and this is remember, the red are protons, you can see it over there. So you're going to put how many you need for your item on the table, and then hit the go button, and it'll see if you made the right one. So how many protons do you need, and how many neutrons do you need? So
10 and it's 10 and 8.
So figure that out. We go down and reach down in there, and
Wait, the blue are neutrons, and then the neutrons are the bottom number, right?
no,
They're the top number.
they're
How
the.
do I get this to fall out?
It's a, you're not writing down anything yet. There's next exercise.
It's the bottom number.
We're going to rotate as teams.
1, 2, 3, 4, 5, 6, 7, 8, and 10.
All right. So then you need.
That's blue.
Yep.
1, 2, 3, 4, 5, 6, 7.
Are you ready? Everybody agree. Now you have 10,
Yeah.
and kind of open up so the camera can watch too. So there you go. There you go.
Wow, you have made neon 18. This form of neon is radioactive.
Which is blue, so it was radioactive.
Positron.
It emits a positron. Let's see what it's used for. Hit the button again.
There are currently no known uses for neon 18.
So
Can you think of one?
and so it's not every radioactive material has a use. And so
I thought neon was like.
Like for like the sun.
it is, but not neon 18. So it's the stable form of neon. This is a radioactive form of neon, but it does exist. So does that make sense? There's some other. There's a lot of radioactive materials in your house. Push it again. There you go.
Potassium 40.
Potassium 40 are in your food.
Potassium is a
Is
required part of your
is
diet.
in all of
That
these
means that you
foods.
are radioactive. Potassium 40 is naturally found in
It's
fruits
in your
and
body, so
vegetables,
you're all
and especially
radioactive.
in
Each of you are radioactive.
Potassium 40
Because you have to have
is also found in
potassium
sports
for your
drinks
muscles
and
to work.
potato chips. Americium 241 is
Americium 241 runs your smoke detector at your house.
Thorium 232 helps keep you out of the dark by lighting up your lantern
It's
when you're camping.
It's just for lantern mantle.
Uranium 238 is used to safely create bright colors and
Tiles and ceramics in your house use uranium.
Dinner plates, glassware. Congratulations on creating an atomic nucleus.
Thank you very much. We're ready to rotate. Thank you. So we're gonna all rotate and then go to the next group. So that's what you had the paper for. Thank you. You guys ready? So we're going to try to stand and leave the center open so the camera can see in here. So it's spread out, and so on either side of the proton or the neutron. Now if you remember, the red are the protons and the blue are the neutrons, how we describe it. And you have your tile somewhere. We don't need that anymore, but you have your tile. Who has the tile? What do you have?
Hydrogen.
So how many protons and neutrons? And you guys are going to set these on the table, and this table can monitor and see if you made the right thing.
One proton,
As a team, you need to agree. So
1 proton, 2 neutrons, and 1 electron.
that's right. So we don't do the electrons here because we're only doing the nucleus, but that's okay. So the balls are in the hopper down below. So and you just put them in the holes and see if you guessed right, or you not guessed. I guess you maybe just know.
So proton, and
Yeah. You guys agree? That's 1 hydrogen 3? Hit the button.
What would you do with the
Well,
atom you created?
it's gonna fall. We gotta do it one more time. That was my mistake.
You haven't created.
All right, go ahead and do it again. That's the reset though, it'll fall through. So, there we go. We're good. Go ahead and hit the button.
Good job. You have made hydrogen 3.
So you made hydrogen 3, you did it right.
Known as tritium. Tritium is a radioactive form of hydrogen that emits a beta.
It's radioactive, so it wants to turn into helium by emitting a beta particle. Hit the button.
Tritium is very rare.
We make this at Savannah River site. We
However,
recycle it.
Tritium can be produced in nuclear reactors. Tritium is used for self-powered lighting.
Like watches, a glow-in-the-dark watch uses it. They use it in exit signs.
An airport runway.
If the power goes out on an airport runway, you want to be able to have the lights self-powered. That's how it happens.
Produce energy and is used as a tracer material in medical and oceanographic.
Does it make sense?
Tritium decays to helium-3 in about 12 years.
Let's go ahead and there's some other
Some
uses.
radioactive materials have industrial uses.
There are
for
industrial
agriculture,
uses.
Manufacturing and construction.
This only goes up to potassium, so there's some elements that are higher than that.
Cobalt 60 helps to preserve poultry, fruit,
So we
and
use
spices.
radioactive materials for
Cesium
agriculture.
137 helps scientists improve important crops like rice and cotton. Cesium-137 also
We
helps
use it
ensure that food and medicine
to-
packages are filled to the right level.
We use it for all kinds of
Iridium-192
manufacturing.
helps make sure welds are strong. And Promethium-147, Thallium-204, and Krypton-85 are all used to measure the thickness of plastic, metal, rubber, fabric, and paper. Californium-252
We use
helps
in
measure
construction.
water content for road and building construction. Radium-226 helps make lightning rods work better.
Congratulations on creating
Good
an
job.
atomic nucleus.
So, thank you. We're going to rotate to the next team. We're ready to rotate, Gary?
What would you do with it?
Okay, who has the disc? We don't need the paper on this one. But let's kind of spread out on either side so the camera can kind of look down the middle. That's pointed over behind you. So now on this interactive chart of the nuclides, or this is interactive nucleus. This is the blue is a neutron, the red is a proton. The balls are in the hopper down below. So you guys have a tile. How many protons and how many neutrons do you need?
We need 6 protons and 14 for 6, that is 8.
Everybody agree? So we need 6 protons and 8 neutrons and put them anywhere on the table, and then we hit the go button. So go ahead and grab them.
6 red ones, 8 blue ones. I'm sorry, dude.
Okay. I think count them, make sure. Does everyone agree? And then kind of step back so we can, and step back so the camera can see, and we'll hit the go button.
Good job. You've made carbon-14.
You did it right.
Carbon-14 is a radioactive form of carbon that emits a beta
So
particle.
it's blue, so we have it radioactive, but it emits a beta particle.
Carbon-14 is a rare form of naturally occurring radioactive carbon.
It's
created
natural.
by the sun's cosmic rays in the Earth's atmosphere. Carbon-14 is used to determine the age of organic materials up to 60,000
So it's in
years
archaeology
old.
is how they use it.
It's also
So
used in medical research.
now there's some other uses. This only goes up to potassium. So we have some things that are bigger that are used in medicine.
Technetium-99.
Technetium-99. We're going to show you that here in a moment.
Thallium-201.
Thallium-201
Used in medical
we use it in medicine.
Indium-111 is another important radioactive material.
And we're going to also cover iodine.
Iodine-131 can be used in medical imaging and
And I'll show you some of these when we go back to the classroom.
congratulations.
Very good. Thank you.
What would you do?
Next rotation. You guys are the last team? Come on over. Over here. And kind of step on either side because we're going to have the camera point down the middle. So step on either side. So this is called the interactive nucleus. This is the table detects what balls you put on it. The red are the protons. The blues are the neutrons. All right. And so you have to figure out how many protons and neutrons you need and put them on the table. So how many do you need? 5 of protons and how many neutrons? 5 also. That's right, because 10. So go ahead and go down below and put them on the table. Good catch. All right, are you ready? Kind of step back and hit the go button. Let's see if you did it.
Congratulations, you have made boron 10.
Boron 10, you did it right.
Stable form of boron.
It's stable, so it's not radioactive, and it's green, it's stable. Hit the button again.
Boron is a hard,
That's what boron really looks like.
and a high melting point.
And we use, it's a nutrient in plants, so it's needed in fertilizers.
Is used as a neutron absorber.
It's also used in nuclear reactors to help control the reactors.
Treat tumors.
So hit the button again.
Other nuclear materials are used to create electricity.
Now there are some materials that are, this only goes up to potassium, so we have some that are higher than that.
Nuclear fuels heat water.
This actually,
create
when you
steam.
come, you can come here on your own time, and this is here available to play with all the time. So you can come here, and this is about how a nuclear power plant works.
Nuclear power comes from the radioactive isotopes. that
So
are
you can
most
see there's
commonly
uranium
used to generate
235,
electricity. In order to control the
there's
nuclear chain
cobalt, hafnium, gadolinium, samarium, all these other items.
reactions on creating
So
an atomic nucleus.
that's how this machine works. So thank you. Gary, we're done when you're ready. We are all done. Okay. Let's.
What would you do with the atom?
We'll all go back to the classroom. I'll follow. You guys can follow me. You have 4 missing?
Well, we got started a little later because we went out there with y'all and
Okay.
then realized we needed to do this.
That's right. There's no class behind us, so we're not in a hurry. So, but if you guys can probably step away, sit back down in your seats. We're going to talk a little more. So you guys, yeah, you guys just pull the bin out of the way, so we'll come back and do it in a minute. Okay, everybody back? So we started out with the periodic table, which most people are familiar with. Who here had seen the chart of nuclides before? Most people haven't seen that before. And so, but it's what nuclear engineers use. What it really looks like, if you recall, it was a big slash, like a big green slash. Thank you. Now, if you hold that. What happens is, this is what we use on the wall. We don't use these big tiles. We just made that where you can actually use it. It's one big diagonal slash, and you can see it actually, this line ends and this one begins, and it goes up here and it keeps going. We only did, the part you made was only to about right here. And so it would be bigger than a gymnasium if we would have done the whole chart with all the elements. And so in this one, the gray ones are the stable, and the other ones, the multicolored ones, are the usable ones, and the white ones are not very usable. And so, but this is, we put this on a chart on our wall like the periodic table, but you can see it's actually hard to read. It's very small. Thank you, gentlemen. We actually have converted it into a book, which is broken into hundreds of pieces that we actually can read. And this is what we use. So if you look, thank you, that's what I was looking for. If you look, it's one big diagonal line. This is the y-axis is the protons, the x-axis is the neutrons, starts down here at hydrogen and helium, goes up past lead to uranium, plutonium. This is the area where uranium, plutonium is up on the chart. And so thorium and uranium are naturally occurring in the Earth, and that's what we use to power nuclear power plants, because they're beyond the line of stability. They're trying to become stable. So any questions on that? So I'm going to show you some uses of nuclear technologies. It's used on how much Coke is in your Coke can. We use nuclear technologies. We use it to determine if a package contains explosives or drugs or weapons, to put insulation on wires, to determine sources of pollution, to find small leaks in systems, to determine termite damage, to determine the age of formerly living things. Whoever had carbon-14 is used in archaeology. That's what it's for. And power for space exploration. In agriculture, we use it to actually irradiate pests. We make materials have much more nutrients, things like rice and things like that, to help people. We can use it to make bacteria in foods to eliminate them, so you get rid of salmonella and things like that, food-borne illnesses. We use it in energy production. In South Carolina, more than 50% of our power is from nuclear power. And so if you have an electric car in South Carolina, your car is actually a nuclear-powered car. Because in Georgia, it's a coal-powered car. So you think it's emission-free, but it's not. You plug it into the wall, and a coal power plant is actually powering it. In consumer products, we have smoke detectors, glow-in-the-dark watches and clocks and signs. We make things where they have no static, like computer disks, non-stick pans, photocopiers. And if you use cosmetics or have contact lens solutions, we make them sterile by irradiating them to where you don't get bacteria in your eye or something like that. In medicine, over 1/3 of all medical procedures use nuclear medicine. And so we use it. This is a bone scan right here, where a person drinks a concentrated drink of radioactive material. The radioactive material goes to their bones. They stand in front of a camera like this, and the radiation comes out of their body, and they can get a good image of their bones. Would you be willing to drink a concentrated drink of radioactive material?
What does it taste like?
Well, it tastes bad. It's not. But what happens is, if you have a problem with a bone, to determine really small problems with your bones, they used to have to cut you open to look at it. So your body flushes the radioactive material out pretty quickly, and they can take that image and it's gone. Which would you rather have? Them do surgery or actually take that drink? And so that's why these diagnosing methods actually reduce the number of surgeries and actually have helped people a lot. We use it in industrial applications. We test welds to make sure welds are strong in cars and airplanes so that they don't fail while we're using them. We use them to find out where oil and gas is underground. We use it the thickness of your cans, aluminum foil, sandpaper, the paper that you use at school. All the thickness is determined by radioactivity. And we use it in construction. Now that's the whole presentation. And so we wanted to show you nuclear is widespread in almost everything we do. And I wanted you guys to see that line of stability and what nuclear engineers do, utilizing that phenomena to push things off or find things that are naturally off the line and use that energy. Any questions? Any questions about nuclear or science in general? Anything? Well, thank you for your attention. I know you're hungry for lunch, so we'll hopefully see you next time. Bye, everybody.